Welcome back to another HVAC-Engineering-Techie training video. Today's video is on the technical commissioning of electrical systems part 1. I had to break this into part 1 and part 2 because it got to be way too long. So we don't want to keep it around 30 minutes, 35, 40 minutes, not get it on an hour and a half. So that's why I broke into 2. Remember, this channel is a channel that talks everything HVAC and electrical, basically everything for building systems. Appreciate you being a subscribing member. If you're not, boy, I really appreciate you becoming one. You just have to hit that subscribe button down below. Give me a thumbs up if you like the video. Painless for you, absolutely free, cost you nothing. No one will ever bug you from doing that. It's just that Google uses that data to evaluate my videos, which actually what keeps me on the air. So I really appreciate that if you do that. And let's get started on technical commissioning of electrical systems. Thanks. So to start this course, I thought I would review what videos pertain to electrical commissioning. There are some that are general in nature that would help you gain knowledge to be able to do electrical systems if you're not an electrician or an electrical engineer. So let's go. First, D10 is electrical system design. Now that's basic design parameters. It's really not intended for electrical engineers, which should have already gone through all of this stuff and way beyond, but it is a primer for basic electrical design. Then S12 is electric motors and drive systems. It's just systems, and it gets you familiar with all the different motors and what kind of drives are available for those motors. S50 is basic electrical. It's just basic electrical, which if you're not done a lot of electrical, you should see this one. And S51 is electrical power distribution systems. S52 is critical electrical power, which is systems like data centers and operating theaters and things like that. S53 is electrical lighting systems. 54 is electrical safety. If you're going to be out there testing electrical systems, you really need to look at this one. Remember that electrical is a life safety system. It's important. That's why it's code driven. Because if things aren't done right or don't understand safe practices, you can hurt yourself. Cx-9 is Technical CX of Electrical Systems Part 1. And this is a pre-functional test one. And I had to break this training series into 2 sessions because it was just too long. And then the next one, X10, is the Technical CX of Electrical Systems Part 2 Functional Performance Test. So this is part testing and this is part testing, but I just broke them. It's just a breaking point. You'll need to watch both of them to understand what's going on. All right. Electrical CX pre-design activities. Certain amount of activities take place prior to design. The commissioning basic process for electrical is the same as it is for mechanical or any other system. The basic process, just all the details are different. So the devil's in the details. So we have a pre-design phase. We have a design review, CX. We have testing specifications. We have commissioning specifications. We have CX site observations during constructions, CX installation inspections, CX testing observations, CX functional test, owner training, commissioning report, and the warranty CX. So this is the standard processes for electrical commissioning. And the part 1, this one covers these from pre-design to CX installation inspections, and part of the observation testing. And then the second part 2, is for this testing and functional test. So right here, these are kind of split between each other. Now, when we get to it, it doesn't really matter whether your test is done up here or down here, just as long as the tests are done. This is just a convenience of being able to describe the commissioning process so you'll fully understand. I'm not sure why, when ASHRAE started all this, they defined PFT, which unfortunately includes 2 different tests, which I'll go over. So pre-design commissioning. First thing, we need to make sure the owner has an OPR, which is the owner's project requirements. Now, a lot of projects don't have these. They do, but they don't understand what they are. It's unfortunate because it's a very good process to do. And basically what happens is the owner is supposed to produce this project requirements, which is the things that he needs this facility to be to meet his needs. So it's really important for the designers to have the OPR, for the contractors to have the OPR, and you as a commissioner has the OPR, because it's the guidepost of what this facility is supposed to do. So it's really important. And so what it should contain, and this is just a real high-level overview, there is building use and space electrical requirements, future power needs, redundancy or backup requirements, quality of power, special systems requirements, sustainability requirements, special materials or equipment requirements. Perhaps this particular customer wants to use square D gear everywhere. So the designer should know that so he doesn't specify Eaton or somebody else. Owner expectations for operator training. So what does his operators actually need training, and he should explain that. Owner's expectation of the design team and their produced documents. So he explains to the design team what he expects to be, what documents are part of the design. Owner's expectations of the construction team, their document requirements. Owner's expectation of commissioning authority and their document requirements. So it's pretty well lays out. This is a real high level. We get much into the weeds. We get much more detailed. And what I've actually done is I've created a questionnaire to give to the owner and say, just answer these questions and it'll give you an OPR. They have to answer the questions. No one else can answer but them. So now, first things the commissioner has to do is one is develop a commissioning plan. It's required in every job, but it's basically going to tell everybody else what you're planning on doing under the job. Because even though commissioning is fairly common nowadays, every commissioner does things slightly different, so you need to explain how you're going to do yours. It includes this commissioning scope, the commissioning team, who are the members of your commissioning team, commissioning team's responsibilities, channel of communications, design phase commissioning procedures, how you're going to review the design. The designers need to know that. Design commissioning forms, if you have any. So design phase commissioning procedures. Explain to the designer what you're going to do and how you're going to do it. And if there's any forms you're going to use, you need to include those. You may not, but if you do, you need to include those. Design phase estimated commissioning duration schedules. Now, you don't know the schedule and you can't determine that, but you can determine how long it's going to take you to do your commissioning of each item. And you put those duration schedules in there so someone can have an idea how long it's going to take. Develop system manual requirements if utilized. Now, a system manual, use this manual. It includes everything an operator needs to know to operate this facility. It's fairly complete, and it's better than, it includes the O&M manual, but it's better than O&M manual because an O&M manual, they're not real user-friendly. I mean, if a manufacturer will do an O&M manual for 10 different pieces of equipment in the series, and never tell on the O&M manual which one's on this job. So it's better that the commissioner provides a system manual. They're big, and we do them in media. We don't do them in paper because they'd be a foot thick. We don't want them to be so large you can't deal with them. But they're really helpful, really good. OPR, the BOD review. Now, the BOD is the basis of design. And that is to be done by the engineer. It's basically a narrative of his design. And the narrative explains how his design meets the OPR. The plans and specifications review, submittals, O&M manuals, and training materials. Editing this was going to be fun. Commission report and electrical testing reports. These are part of all the commissioning plan. You're explaining exactly what you're going to do and what these materials are going to contain. Commissioning of the design. Okay, let's go through how you commission electrical design. You should have a design kickoff meeting, and normally I have one that includes all the systems in my scope of work, so it would include all the engineers from those scopes of works, because they're all things are similar, but we go through each discipline separately, review the basis of design that the engineers provided. Now, I got to tell you, most of the time you won't actually get a BOD. The engineers kind of don't quite understand what's going on there. But if you've done your job with your owner, he will insist that they do a BOD. You need to create an issue log. Now, issue logs are normally separate for design and separate for construction. And the reason is most designers have an issue with contractors being able to review their design review issue logs. And the reason is because they feel like some contractors might exploit an area if there's been some issue with it in the past. Not sure why, but it makes them feel much better if you have a separate log. Design review, you perform a schematic design is in the compliance with the OPR. So number one thing you're looking at, does this design work? Now, normally in commissioning, we have several design reviews. You can have a 35%, 65%, 95%, and 100%. Normally, we only see a 65, 95, and 100. If you have a 35, basically that's just to look at the schematic design you gave the owner when they were proposing a system, so it doesn't include much meat. 65 design review looks at basic plan for power and lighting distribution, testing specifications, commissioning specifications. You got to have an electrical commissioning specification, electrical room locations and layouts, and we need it. We need the layouts early because we need the electrical room locations and layouts early because other crafts need to know where they're at and what they look like. For instance, the HVAC controls normally wants to put control panels in an electrical room, so we need to make sure there's enough room for that. And maybe fire alarm panels might be in the same room, so we need to see them at 65%. All code required calculations, load balance calculations, coordination studies, the protective device settings, short circuit analysis. This is normally all part of the coordination study, but we need to have that data because the contractors need that data. We want to check it just to make sure it's okay. Site plan lighting levels. Normally they'll have a lighting level plan required by code on that. Riser and main layout. So you're going to look at a one-line diagram. So here's a one-line layout, what it looks like now. Of course, one lines, none of them look alike because they're all different systems. But basically, a one line shows the main entrance switchgear and the main switches, goes out to panels and what transformers there are, what sub-panels there are down below that. If there's a generator on site, then there's an automatic transfer switch to some panels. And we just have different layouts to whatever their loads are. Now, there is actually a better way to lay out a one line. On every single project I have to broach this subject. Does the owner want to have sub-metering on the job so they can manage their energy? If they want to manage their energy, then this layout does not work. They need to do a sub-metering for building efficiency, which is a one-line diagram that has meters. So what this causes and why the engineers provide a lot of grief for this is these are non-segregated. These are integrated panels. So these panels may have plug load, lighting load, and HVAC load on the same panel. Well, if they have that, we can't adequately manage energy. And the reason is because of all the loads, the only one an operator can actually affect really is HVAC. How they manage the HVAC system, how they maintain it's really important for energy. But if that energy is buried with plug load and lighting load, then it becomes much, much more difficult to tell when you make a change or you make a correction if it actually did any good. So what we want to have the panels, instead of all these panels coming back to the SES, we want to have a distribution panel for each separate load. So you'll notice this is actually a plug load. This is lighting load. This is emergency life safety special loads. And this is HVAC loads. Now, HVAC loads, it has a high voltage panel here that can take care of it, or it might, if it's a big job, might have a full distribution system for the high voltage, the 480 volt. And it might have another distribution for 208 down here at 120. But irregardless, we need it. So we're going to put a meter right here. So this meter will catch all these loads, both the high voltage and the low voltage. And then we're going to put a meter right here, which will include all the lighting loads plus the HVAC loads. So to get this one, we just have to subtract one from the other. And then we have no other meters except the main meter. So if we take the main meter, subtract these two, we get this load and the life safety load. We get the plug load. And life safety is part of plug load. So that will give us determination of what's going on. Now, I say this in the design process video is that when I first started, HVAC was normally about 60% of the load, and lighting was about 2.5 watts a square foot, and plug load was below half a watt a square foot. Well, nowadays, that's all reversed. Lighting is down below half a watt, and plug load is way above 2.5 watts. Remember, plug load is anything you plug into a receptacle, including data center, data closets, your network infrastructure, all that sort of thing are all on plug load. So you can't actually do much with plug load. I mean, people won't let you unplug stuff, so you're pretty well done. And lighting, the only thing that happens with lighting is schedule. So once you get the schedule set, lighting isn't going to change, but HVAC does. So this metering is really important. Now, you can do the metering many, many different ways, but the time to approach this is at 65% before the engineer spends a lot of time laying out integrated panels when we need segregated panels. So that's really important. All right, design review, 95% review. Well, then, you do the 65%, you send in your report. The engineer needs to look at those and respond to your comments. Sometimes you have a problem here when the designer never responds. And if that's the case, you need to get the owner involved to say, please make sure they've actually looked at these. Now, because the engineer has all the authority, they may not agree with your comments, and that's fine. We just want to make sure they've looked at them and understand what we're talking about. We're going to look at the final plan and specification document reviews, review all that stuff, review for coordination, schedules, and adequate information for constructability. Electrical mechanical equipment coordination. Does the electrical actually have a list of all the mechanical equipment that he's got to feed and what size they are? Because one of your chores is to make sure the mechanical load matches what the electrical load says. In other words, if this motor, the mechanical, this motor is 480 volt and the electrical shows a 208, you have a problem. And that's why they need to be on the schedule so you can see them. Electrical and plumbing equipment coordination, same thing. Electrical structural coordination, we're just make sure the structural drawings have looked at anything that needs to be supported on the electricals. May not be many things that need to be supported, but maybe it's structural coordination. Same with architectural. Review of a specification for testing and commissioning. Want to make sure that they've included what you've given. So that's important. Drawing review. Use the inspection checklist that follows to review drawings for basic requirements. In a minute, we're going to go through a checklist. It's not a real intensive checklist. It's just the things a lot of people overlook. Review drawings for code-required drawings. The AHJ, which is the authority having jurisdiction, will conduct life safety code compliance reviews and inspections. So we don't have to worry about that. They will do that. Review layout for code compliance. Now remember, as an electrical system commission, you are not responsible for code compliance, but you need to review the drawings for major code issues for layout. If no one notices these issues, they cannot be changed later. So it's important. Now, the ones I'm talking about, there's a lot of code items that are important for operators and that helps them actually manage and operate the systems and safely. They're things that the code officials normally ignore because they're not that important to life safety. The code guys are really needle focused on that life safety issues. And so we need to fill in behind them to make sure the other things that they normally ignore are actually looked at. Someone actually looks at them because they are important, but a lot of times they get ignored. This is a way to show value to the owner. The following code review items are not critical life safety issues, but directly affect operators and operations and are normally overlooked by the local, just what I said. So we want to make sure we look at those. If you discover any life safety issues, it must be reported in writing separately. This is not just in design review, but even when you're out in the field. Never put a life safety issue in an issue log because it's something that needs to be addressed immediately, so you do it with separate communication. All right, so here's these code reviews. Now, I'm not going to go over and read these intentionally. If you really want these, you can stop the video and snip this out. But cover sheet, this is kind of going through the general things. Usually includes a simple schedule sheet. And it's really important on that schedule sheet that they actually update it for the project. Many times this is a standard sheet that includes their standard symbols the designers use. And then later on the drawing, the designer uses symbols not on the sheet. That's not good because you can't figure out what they're trying to tell you. So you need to look at that. Generally, a power site plan, generally reviewed for site, underground systems, electricity. Verify all miscellaneous items. Just want to make sure that the site plan includes what it should and coordination between other crafts. The site lighting plan may be a part of the power site plan, but generally it's a separate drawing. And this includes, there might be two drawings. It includes all the site lighting, but it includes a lighting level diagram that's required by code. Power floor plan, all power distribution equipment, panels, transformers, switchboards, located on the floor or in same elevation as the FFE must be shown. Check floor mechanical equipment against mechanical drawings to assume that all equipment is shown and circulated. So you want to make sure that the electrical has picked up all the mechanical equipment. First floor power plan should location of incoming domestic water lines and fire riser lines. Now there's been a code change here. One of the code requires that the electrical grounding be grounded to the incoming water. And it used to be the fire line was also included, but that has been deleted. So nowadays, fire line is not required for electrical entrance. Lightning protection. If there is a lightning protection on the building or structure, there are usually separate drawings for this discipline. They will generally be at least two drawings. The first will show the building or structure and equipment, ground rods, counterpoints, downloads, wiring, sizing. The second drawing will have all the details and specialty notes. The first drawing should be indicated as some manner either by little bitty words, home run from a download or by a keynote. So normally, lightning protection is done by a separate engineer. There are specialty guys out there who do nothing but lightning protection, and they'd require some calculations that's just much simpler for the owner and for the design engineer to hire a lightning protection company to do the design for them. That's normally done. Roof plan. This is normally a large amount of equipment, so you want to make sure you have a roof plan. Verify there are weatherized receptacles from 25 feet of each piece of heating and air conditioning equipment for maintenance, or else maybe the HVAC unit has a power coupling inside of it, a power receptacle inside the unit. The only problem is you want to make sure that that receptacle is not fed from the unit power, because when you're working on it, you have the unit power off, so it needs to be a receptacle that's on when the unit is off. Floor plans for lighting should show the fixtures, exit lights, and any calculations. It should be specialty systems. Now there are other systems, and I have other videos covering communications and fire alarm and security and that sort of thing, but they should be separate drawings for those. One-line diagrams. It should have load calculations and fault current calculation. Normally won't be on the one line, but those need to be available. When a one line is shown, they should have already done these calculations. The SES, which is a system entrance service, it should be identified with what size it is, its voltage. So we have panel schedules. We'll have all that. We'll have transformer schedules, we'll have grounding, and the grounding should be shown. So anyway, just the general stuff for a one-line review. Panel schedules, look for load description for each breaker. So there should be. So when they do when the designer does a panel load sheet, he will actually list all the circuits. Well, the IDs on those circuits need to be accurate. Tell exactly what piece of equipment this breaker is for, and what current those breakers have. And then you need to look to make sure the schedules are balanced. That code requires that the legs of a panel are within 10% of each other. So if they put single-phase loads in a three-phase panel, you need to make sure those are on the right legs to keep that panel balanced. Schedules shown include fixture, mechanical, and plumbing powered equipment, specialty equipment such as kitchen equipment. Fixture schedule show mounting heights. specialty fixtures such as high bay fixtures and any height of pole lights. Details, you'd have detail sheets doing different wiring. Now, one thing that's when you always look, no matter what discipline, when you're looking at a set of drawings in the design, what you're trying to determine, you're not actually checking the engineer's work. You're actually checking, does the drawings communicate the design? Can an electrical contractor actually build this job from this design? If you can't figure out how to build it, they probably can't either. So that's what you're doing. You're trying to help them put up a set of drawings together that actually communicates what they want the contractor to do. And that includes details. Are there adequate details that show us what we want to do? And electrical, a lot of times, fail that. For instance, if you have a hydronic mechanical system that has a cooling tower, you will almost never see a wiring diagram for the water treatment equipment, which takes 110 volts. So it should have a wiring diagram. A lot of times that's just left in the open. And you get down to the job and then no one's got the wiring in, so now you have to figure out who's going to do the wiring and is it an extra or not. Things like that should be included in electrical. For instance, controlled HVAC controls needs 120 volt power. Well, those should be identified on a mechanical plan so the electrical designer knows he needs a circuit to feed that control panel at that location. And if those aren't provided to him, he can't do that, so it needs to happen. Then, of course, you need to look at electrical specifications. Need to make sure they have a specification for everything that's on the drawing, and that they don't have a lot of things in the specification that aren't used on the project. That is irritating sometimes when they just use a base spec and they don't actually look at it to make sure it matches the job. You should only have in the spec what's actually on the project. Layout, this is working clearance for electrical equipment. This is one of the things that we watch because the code authorities don't seem to pay attention to this. Remember, if you have 150 volts or less, the code requires 36-inch clearance in front of the panel for the full height of the floor. For higher voltage, for above 150 to 600, it's 42 inches. So it's quite a bit of room, and this includes any panel that has power to it. So it includes VAV boxes if they have 120 volts to them. If they have 24 volts to them, this code requirement doesn't apply. But to tell you the truth, when you're doing mechanical, everyone needs to get to the equipment, so you have enough space to actually get to the equipment. But this is actually a life safety issue, and what they're trying to do is they're saying the code actually says there can be no grounded component within that space. So in other words, if you have a disconnect switch above the ceiling, that has to have 36 inches in front of it from that device clear to the floor. You can't have a conduit in that space. You can't have a sprinkler pipe, something that is grounded that a technician can lean against. That's why. And that's why it's important. It gets irritating because no one looks at this, but this is there. Panel housekeeping pads. This is another thing that people don't tend to look at, but is a code requirement. All the panel gear in an electrical room that's sitting on the floor needs to be on a pad, housekeeping pad, and by code, that pad needs to be the same size as the gear. If the pad is bigger than the gear, now it can be an inch. No one's going to complain about that, but if it gets to be 6 inches or more, the code requires that a tripping hazard. They don't want anybody tripping, so then the pad needs to be that 36 or 42 inches. So it's really important that the contractors get the pad the right dimension, and if they don't, then that panel needs to move to the front of the pad and not to the back of the pad, because that up front will be a tripping hazard. We see that all the time. Sub-meter locations, if you have meters, where are those meters located, need to be on the design. All right, let's go talk about testing specifications. Now, this is something that's normally overlooked, and it's something that needs to be in there. The electrical specifications are reviewed to make sure the electrical specification contains detailed testing requirements for testing the electrical systems. These tests are described by the NETA, which is National Electrical Testing Association, Acceptance and Testing Specifications. Now, I'm still using the 2007 version. I don't think they've changed much, but they might be. But here's the thing. Some engineers will say just test the system according to NETA standards. That's not acceptable because NETA has hundreds of tests. And if you do that, the testing will be exponentially expensive and not necessary. So you need to actually, because they cover every kind of building in those tests and every kind of occurrence, which you just need the tests that we need to have for this building. So the testing specification should detail which tests are to be performed, what equipment is to be tested. So in other words, it'll make a list of the types of equipment and what tests are to be performed. And normally they will be, this is a normal list, but may not be what the designer thinks they need or the owner thinks they need. Voltage and current testing and documentation. So when we heat up panels, we make sure we have voltage and current everywhere. Mega, high pot, and high pot insulation resistive testing. So we're going to test cable and wire and equipment to make sure the insulation is correct for the voltage of power we got going through it. Bolted connection resistive tests. These are always done. Circuit breaker injection testing, either primary or secondary injection testing. And this is something the engineer and the owner has to decide. Now, normally, we only do injection testing on a larger circuit breakers. Normally, I've seen specs that only does things over 250 amp or maybe 300 amp. And down below, they're not. Or maybe it may go down to 100 amp, but it depends on the type of facility. If you're doing a facility that's critical, like a data center or something, maybe they'll injection test clear down to 100 amp. And there are two different types of injection testing. Now, this is where they take a circuit breaker and they test its trip mechanism to make sure it actually works before we power it up. And there's primary injection testing, which basically takes the circuit breaker out of the gear, places it on a stand, and has a machine that injects overcurrent to the device. It actually puts overcurrent on it, and then they record and watch what the trip mechanism does. And it's at that time it's verified that it is in accordance with the coordination study. There is another way to do that, and the reason is the manufacturers say that primary might actually damage the circuit breaker, because when they do it at the factory, now all circuit breakers are tested at the factory, but it's done under sterile conditions. It's done at a certain temperature. It's done at a certain humidity. It's done at very close tolerances on the power. Doing it in the field, those conditions are not there, so it may actually damage part of the circuit. So there is another way, and it's called a secondary, and secondary only tests the trip mechanism. It doesn't put full current across the switch. It just tests the actuals, the basic circuit. The secondary injection doesn't test the whole switch. It just tests the breaker part, the part that drops the load. And these are not dangerous to it and are cheaper and easier, of course. But some people want to test the whole one, so depending on what they want to do, they need to specify primary, secondary, and at what current they want us to do it. Normally it's in the amp rating, and it's either 100 amp, but you would never do lower ones, but you would normally, I've seen 250, 300 amp being the lowest size. Thermal scan of all devices and bolted connections under load. This is the gold standard for testing your system. A lot of commercial jobs, I don't do this, but on more critical jobs, they certainly do this. And this is where you can catch really fine details of issues before they become a big issue. Phase balance load survey to make sure the panels are all loaded between phases. A 72-hour power quality study. And this is what I like to see once the building is occupied and it's under normal load. We'll do a 72 power quality to make sure we have no power quality issues at all. And to do that, you have to do it with a power study. For standard systems, the CX specification may include contractor install field inspections, required check sheets and forms, bolt torque settings, field verification and what forms are going to be used there, resistive test and what forms are going to be used there. And these are all pre-functional tests. This is before we heat a panel up, so these are all done before that. Equipment startup and test reports. These are the second part of a pre-functional test. It's getting it ready to heat it up and testing it while we're heating it up. Functional performance tests. Now this is all in the design review, right? So functional performance tests, how are they specified? And they're thermal imaging of operation gear and connections. This is a little bit more intrusive than you think because you have to put the system under load. So you have to bring in load banks to make sure the circuits are at design load and then you thermal test them. No good to thermal testing if it doesn't have any load. I guarantee it's going to be fine. It only happens when it's under load. So main panel 72-hour power quality test needs to be done when it's occupied under normal load. And you're looking for voltage, current, load balance, power factor, harmonics. So you're looking at all that quality will come off a power quality meter. And 72 hours is a real reasonable time period for that. Critical system testing, that's full load testing. UPS system testing, that's under full load bank again. Battery drawdown test on UPS systems, these all need to be specified. Generator testing, and that's an NFPA requirement. It is at level 1 or level 2. This describes whether it's a backup generator or emergency standby generator. And they have different requirements and different testing requirements. Vendor or contractor test report. Now, normally all this stuff is all done by a contractor. It may be a testing contractor. One thing the spec should say is, in this testing specs, is this job requiring a third-party independent testing agency. Many specs do. They require a NETA certified testing agency. Now, NETA is more than an association. It basically certifies technicians to a level of testing, and it's really good. If you get a level 4 NETA test technician, you got a really good guy. Well, at least he should be, because he's got the knowledge. So that needs to be in there, and these are normally, these critical system tests are normally done by a third party. There's no reason a contractor can't do it if he has the people. So 100% CD reviews. The others were DD reviews, design documents. These are design CDs, these are construction documents. So this 100% CD is ready to go to the contractors to build a project. So you review this you verify the final plan and specification documents are ready for construction. You verify the previous comments have been included in the design documents. You verify the design documents are fully communicates the design. Can they build it from these drawings? The commissioning's main focus is the maintainability, commissionability, operability, and functionality of the electrical system. And that's your focus. It's not the same as the contractor. It's not the same as the designer. But this is your focus. These are all things that the owner needs when this job is done. So now let's go look at what happens when the job actually starts. We're under construction. This is easier, better stuff. First of all, you have a kickoff meeting. And this is a kickoff meeting for the contractors. You produce an agenda. You have your commissioning plan. You're going to review that. You're going to do submittal shop drawing review, explain in your kickoff meeting. And when you do your plan includes all the stuff that we did earlier when we talked about the plan. And then you're going to talk about how you're going to do submittal and shop drawing reviews. These are important to be done because you need the data off of them if you're creating check sheets and forms. It's a technical review, data for electrical system testing criteria procedures, data for check sheets and forms. That's why you're doing these submittal and shop views. Then you're going to do site observations and inspections. Installation meets the OPR functionality and maintainability requirements. Pre-functional tests and functional tests. Electrical commission tests are broken down between installation inspection, system startup, and final functional tests. We have 3 types. We have a PFT, and I call it an A because they didn't. And that's for the installation inspections. That's pre-startup. And the B are the tests during startup. I should have called it something else, but they didn't, so I put a Part A and Part B in it so we know what they are. And the functional performance tests, FPTs, are the final system performance documentation. So the FPTs are mechanical, are really difficult. FPTs and electrical are not that difficult, but they have a lot of data that needs to be recorded so that everybody knows what these systems looked like when they were brand new. Okay, power distribution pre-functional tests. This is the PFTA. It's a contractor or CX to inspect and record record installation requirements. So now this can be done by the contractor or the commissioner can do it, but normally this is done by a contractor, and he documents it by filling out a check sheet. Installation according to documents, size, location, alignment, and anchorage. This is the right piece of equipment in the right place. Cable raceway installation is done and inspected. Cable mega installation testing, if it's been specified, has been done. Equipment and cable high pot testing is if specified. Circuit breaker primary or secondary injection test, if specified, has been done. Connected bolt torque settings have been done and verified. And then verification record form, to put everything on a record form. And then normally what happens if the contractor does this, the commissioner will kind of fall behind and make sure these are actually been done. And we normally always check to make sure all the bolt have been torqued. And the way you do that is the contractor, according to the spec, the contractor is to put a Sharpie mark through the contact once he's torqued it. Once it's torqued the right time, he does it through the bolt, the nut, and the plate, so you know it hasn't been moved. If someone comes by and moves it, that line will not be together, and you'll know right away someone has moved it, so then you'll have to call for a retorquing. So there's some things you can't check again. All right, now this one's a little maybe detailed, but I had to put these together to kind of inspect. When a contractor builds this raceway system, puts his conduits up, he'll put hangers up, and there might be trapeze hangers. And if they're trapeze hangers, there was a problem because how are they adequate or not? I mean, I've been on jobs where the trapeze are bowing 2 or 3 inches, which means they're way overloaded. So basically, this is a chart here just so you can watch it. This is conduit supports. This is what the code says for how often these different things would size. And here's the supports between centers. So it tells you if you have a 1/2 inch rigid, it needs to be every 3 feet. You have a 1/2 inch EMT, it's every 10 feet. So this tells you that. And then this is the weight, average weight of a fully loaded 1/2 inch conduit with EMT. It'd be a 1/2 pound per foot. And that's with maximum fill. So you're pretty well guaranteed that it's going to be slightly less than that. Not much, but slightly less. You know, if you have a 4-inch conduit and it's rigid, it's going to weigh right at 20 pounds a foot. It gives you an idea how much weight's going to be on your hangers. And then if you inspect a hanger loading, this is what I'm talking about. This is a trapeze hanger, and they'll put conduits on both sides of it and run it through it. And this is all perfectly fine. Now, there's one code requirement that says no other trade is allowed to hang anything from an electrical hanger. And the reason is because there's no way to know what that other thing weight is. So this is what determines it. This is unit struts. These are the different unit strut. Now, I know it's a proprietary document, but anyway, these are the sizes of the U-strut, and these are the loading. This is the maximum loading on these. Now, this is really conservative safe. And this is the span, and you'll see a lot of these can't go over this spacing. And then this here is for angle, C-channel, and I-beam. So these are bigger ones. You can do it, and this is like a 6-inch channel. And you can see this is the weight it carries at these devices. Now, these are for you to make. Now, the other way to do it is engineer design. And this is really the preferred way, but not many do this. So if you have a really big hanger, normally a structural engineer will need to just pipe in and say, here's my calculations for sizing this beam, because it matters if it's distributed load or if it's all in one place. That makes the beam slightly different. So these are all conservative, and you can use these just to do a slight check on this. But you know, in the end, the contractor is actually responsible for this. So if he overloads it and it bends this member, you should punch that. That should not be acceptable. So here's an installation inspection, which is you're going to do for a panel. And the things you're looking for is a panel wire management. Does this wire management look like this? You know, you just don't want it to look like a garbage mess of wire. It needs to be well thought out, well managed. It needs to have wire bracing. Now, the reason this wire bracing is in here is if there's a short circuit anywhere, that wire will try to straighten up. It will physically move. So you need to have it constrained so it cannot do damage within the panel. Wire color, taping, or colored wire. I've showed colored wire. It needs to be, if it's all black wire, it needs to then be taped what the actual color is, and that's called wire taping, and you can do that. Now remember, the colors are dictated by code, and that's reviewed later. Wire tags. to make sure all these wires are actually tagged at what this tag is, and then these lists. This is the breaker list, and these are the breakers are numbered in the panel. These are really, really important, so you need to make sure these are actually done. They won't be done right off the bat, but before this panel is done, that wire needs to be typed and put in that panel, and it needs to be exactly what that load is, not, HVAC. No, it needs to say this is air handler 4 or whatever it is, or fan coil 2. Cannot be generic. It must be exact. Panel and circuit labels. So the main label on there, and these labels are dictated by what the specification says. This is how what we're going to follow for labeling. All right, so then in a transformer, same thing. We're going to look at transformer wire management. Now, why I'm saying wire management, some panels are different. Some transformers will not allow wiring above these transformer coils. See, this one shows wiring entering and going out the top, and some transformers are rated that way, but some are not. So this must come down and go out here below. And the reason is because this is a high temperature area and it gets hot. I mean, I don't know if you've ever noticed, but transformers that are under load generate a lot of heat, depending on their efficiency. But it can get up to 180 degrees up in here. So it can be hot enough to damage the insulation on a wire. So that's why it's that way. Wire bracing, again, there's wire bracing here, and that's to keep this wire from moving when there's a short circuit. Wire color taping, the same thing. These wires in this one, you'll see they've been taped here and here. The colors are taped. And transformer grounding. Now, grounding is very important to transformers. Transformers normally require a continuous ground, that the ground wire goes from one transformer to another back to the actual entrance ground and to the ground rod, so that these transformers are fully grounded. There can't use conduit to ground them. They have to have a separate ground wire. And of course, transformer label. Okay, here's the kind of those code issues again for field inspections. We'll just go through these quickly. Depth of conduit, make sure there's a table in there somewhere that says how deep conduits are buried, if they're buried. Conduit spacing in an underground duct. An underground duct's a concrete duct that has conduit within it. And there is a spacing in it, and it says basically they have to be buried deeper than 18 inches. And the spacing here is 3 inches between conduits if there's 3 or more conduits in the spec. Housekeeping pads, I talked about this earlier. The housekeeping pad needs to be the same, so you need to field inspect that. Conduit supports, do they meet that table of every 10 feet or whatever it is, the one I had earlier? A flexible metal conduit should be supported within 12 inches of any termination and a maximum of every 4.5 feet. Similar requirements exist for liquid-tight flexible conduit. So, I've seen people that run 12 foot of flexible conduit that's not attached. It's not acceptable. It needs to be, some specs are 6 foot or less, or 4.5 foot or less. Need to make sure those. And another thing about flexible conduit that's not a code issue, but liquid-tight is not UV protected. Liquid-tight, the sun will eventually eat the plastic upon liquid-tight. So it either needs to be shielded in the shade or it needs to be painted. That's one thing no one tells you. It looks better not painted, but if you want it to last for many years, it needs to be coated. Boxes and conduits above ceilings shall be supported independent of ceiling wires. Can't hang anything off ceiling wires. And electrical should not hang off any other craft's hangers either. Other crafts can't hang off theirs, and they shouldn't hang off other people's also. Unless it's like a structural frame underneath the piece of equipment, fine, you can attach a conduit to that. Disconnect switches location, all disconnects should show where they're located, and it should be located so they're accessible. Have safe working distance, 30 to 36 inches in front, for under 20 volt, 42 inches for anything above, just like anything else. Exposed wiring systems shall be installed manually. Okay, this is low voltage wiring. Normally applies only to HVAC or electrical security. Electrical connections, all equipment should be installed according to labeling, which includes including termination wire attaching a bus splices with a giving tightening torques. You're going to make sure these are torqued. That's any bolted connection. If it's crimped, of course, it doesn't need that. Breaker layout design. Equipment and circuits are de-energized shall be rendered inoperative. All switchboard circuit breakers should be equipped with a permanent mounted manufactured provided lockout device. This applies to the bigger ones, of course. And if you're a smaller circuit breaker, they have circuit breaker locks for those. And this is a way to lock them out so that an operator can lock it out so no one can turn it back on. Multiple services. If you've got a piece of equipment that has more than one source of power, it has to be labeled that this has more source of power so the technician can know that, it gets, even though this disconnects off, it can still have power. Disconnect switches with permanent labeling indicating equipment name, organization of feeder, voltage, and phasing. Panel schedule labels, we've talked about that. They need to be complete. Site panel, pole position indicators. Every circuit and circuit modification shall be identified as to its clear, evident, and specific purpose of use. So just make sure they're labeled correctly. Signage required for generator-provided equipment. So if you have a separate source of power, which is an emergency generator, they need to be listed that they have that source of power. So someone doesn't assume, well, the power's out in the building, I don't have to worry about it, but if this is on emergency power or standby power, it does. Then grounding. You want to make sure the grounding indicators has a continuous ground or ground feeders as is required. You want to also make sure that ground has been tested with fall potential tests to make sure the ground rods are sufficient. And then this is my electrical inspector. This was his pet peeve, so it's gotten all my documentation. When you have an electric water heater, code actually requires that both the hot water and cold water be bonded so the ground will pass, because hot water heaters have dielectric couplings on them to keep from damaging the water heater with electric currents. So an electric current cannot pass from the cold water to the hot water main through the hot water heater because they're dielectrically isolated. So there needs to be a bond wire from the cold water pipe to the hot water pipe, as long as they're metallic, so that the hot water pipe will be fully grounded. And that's actually a code requirement, but this is one that no one ever looks at. Okay, power distributors pre-functional test. Pre-functional test, this is the A test. Contractor to inspect and record installation requirements by inspection. Equipment is the same as submitted with correct components. Install according to documents. Raceway install correctly. Cables and termination install correctly. Panel labels and cables tagged as specified. Contractor to inspect lightning protection systems and ground systems and record installation requirements by inspection. Equipment is the same as submitted. Ground continuity and fail of potential tests. Now, this is really important, this ground test. This is how they test ground roads. And what they do is they set up an instrument, and it's a special resistive instrument, and you hook it to the ground rod, and then you put probes in the earth ever so many feet away, and I think it's every 10 feet. You put that away for 30 feet, and then you do this test. And if the ground rod is not sufficient, the ground fall test will not pass. Now, you got to be careful and don't let a contractor pour water on it, because that's not allowed. You pour water, it'll work fine. There are different kinds of ground rods. If the soil is so bad at conductivity that a single ground rod won't work, then they'll put a mat down of number 4 wire or bigger, maybe aught wire, and that's a ground mat, and that might work. Or if worse comes to worse, you can use a salt ground rod, and what that does, they drill a hole, and they put a perforated pipe sleeve down in it. Then they put the ground rod down, and then they fill it with salt. And then they pour water on it until all that salt actually dissolves. And then they have that back, and then the pipe's the ground rod. And what happens is, as the salt goes out into the soil, it takes the salt with it, which is conductive. So it makes that hole much larger, so maybe 2 or 3 feet in diameter where it's conductive. So that can work. Those are expensive, but they can happen. And then bolted connection resistive tests, those always happen. They have a test form. It might be one of theirs. It might be one that you've generated. The check sheet basically says it's for, you're going to have one for switchgear panels, transformers, generators, ATS, grounding system, power management system, lighting control system, all electrical equipment. So these check sheets are for all equipment, and they're basically a way of verifying, yep, I've done this. And you don't say a check mark. Basically, you put data in there, the actual panel number, the actual number of circuits down here, all that sort of stuff, or else you say verified, I've checked it. So you know that it's actually done. And these are the contractor's verification, and the contractor has a signature down here to sign on the line. And what these are all done, verify the installation, contractor's quality commitment. If these are done really well, and you can tell the accuracy is really good, then this particular electrical contractor is really serious about quality. And then the commissioner is to kind of verify, go back after him, verify a few of them, just do it by spot checking just to make sure he's doing the job correctly. And here's some typical electrical system inspections. These happen to be some fairly big pieces of equipment, and you'll notice this pad is 42 inches in front because it's bigger than the equipment. This happens to show water lines. This is not allowed. It's against the code. No water line can be above a piece of switchgear. This picture I put in just to show you. This happens to be the biggest piece of gear I've ever touched. It's 4,000 amps, 12,000 volts. It's a substation coming in a high-rise building. And I was there. This was an existing facility, and I'm doing an existing facility commissioning, not new commissioning, but I noticed a tarp over this piece of gear. It's a substation, and it's dripping water down off that because there's water coming out of a duct. There's an air conditioning duct above this, and it's dripping water. And to say I panicked is the correct thing. I said, this is a 4,000 amp. It's on, under load. I ran and grabbed an operator and said, what's happening? This can't be. He said, well, we put plastic up so we wouldn't get it wet. I said, you don't understand. If water, this is right above the transformers, if this water gets in there and this blows up, this will actually take down this high-rise building. This is more energy than you can imagine. They don't allow, most buildings no longer allow 4,000 amps. You can't have anything bigger than 3,000 amps, but 12,000 volts at 3,000 amps is a big substation. And I couldn't believe that they were letting the operators just didn't think it was a problem. Anyway, I got a lot of people excited about that right away. That's one of those life safety issues that you need to let somebody know. I didn't have time to write a letter. I went and got somebody. This is a main service entrance. It has meters. It has big switches. This was a wiring panel. This is the back end of a piece of switchgear. Shows you the cable. This was a big job, and they use colored cable. A lot of times they won't. They use black cable and just tape them. Now, when you're inspecting these cables, the one thing you want to look for is if there's any damage to the cables by pull. They use machines. These are big cables. These are probably, 2 or 3 aught. So they will actually use a machine to pull this, come along with a machine and pull this out. And if they over pull it, it'll damage the sheath of the wire. And that can be a problem if they've damaged the wire. You might have to request they remegger the wire after they've done that. And there's the specifications for cable has certain pull strength. You can't over pull it. But if they over pull it, they'll damage the exterior sheath. And if they do, that's a problem. These are another pull station coming in. You see this is pull. This is an ATS switch. And this happens to be a bus, a vertical bus. Sometimes if it's a high-rise building, they'll use a bus like this, a vertical bus, and they have switches on the vertical bus that pull power off instead of using conduit cable. Transformers can be mounted high, not a problem. They just have to be accessible. And that's basically it for part 1. Part 2 will get into the actual testing of the system a little bit more. So I hope this wasn't too long, and I hope you enjoyed the presentation. Really appreciate you watching. Have a great day, and I will catch you on the next one. If you have any questions, remember to put them in the comments. I do answer those every couple of weeks, Don't look every day, but I'll be glad to answer your questions. Thanks. Have a great day.